everyone, how are we doing? Gonna get started here and do a little 320 review. I've got my Canada Dry, which is being obliterated by the, oh, you can see it. Kind of see-through right there, kind of see-through. Yeah. Making sure. Hey. Need cough drop. Ooh. Aye. There we go. So, let's take a look here. Let's talk about what's on the test. Okay. 7. Let's go take a look. Here we go. Wrong button. Okay, so this is the test bank where your questions come out of. Multiple instructors have helped make this. I see my name on a few of them, and maybe if it doesn't have a name, it's probably my name. Thinking of Nana Bryan right there, Dr. Bryan. Amazing work on those. It's kind of a mixed group of things, different questions, multiple choice. So it's kind of your mixed bag questions. There's like 8 questions in there. So a lot of different things. That one's not as descriptive, I would say. Even I had to double check to be like, what's in there? It's like, oh, it's a bunch of like random stuff. This one here, interpretation 2 indicators. So I think it's pretty clear. Interpreting indicator variables, those are written right there. So you get one of those worth 3 points. That's pretty hefty right there. Interpreting indicators. We have interpreting multiple regression right here. We're gonna interpret with multiple regression. Those are written interpretation, multiple regression. Interpretation of logistic. So you have to know how to interpret a logistic model. We've done a lot of that. There's the mixed bag. R output. So you have to know how to read R output. 4 points from that. And there's, I think, 48 points on the test. How many is there? It's like 48, 46 points on the test. Make sure stuff wasn't on here that we didn't cover. Logistic regression output. So once again, output. Hey, Olivia, good to see you here. I had a cough drop. I have a cough drop and I have Canada Dry. I'm congested and I haven't shaved in a, see, look, it looks like winter. This is winter Canada Dry. Haven't shaved. It says see-through can. Hey, Alan, good to see you. Hey, Alan, haven't seen you in a while. Good to see you, Alan. Let me say hi. And logistic regression output. So you have to know your output. Confusion matrix. We actually did a confusion matrix yesterday. Do you know what a confusion matrix is, Olivia? Like, what is a confusion matrix? Throw some points out here. What is a confusion matrix? It's run by the code confusion matrix. So, what does a confusion matrix show? And we did calculations on this in the last class, I believe. So, or it was either the last class or second to last class. We did calculations using a confusion matrix. So, hopefully people remember what one is, because there's specifically numeric entry on a confusion matrix. And there's things we can calculate from it. So when you look at a confusion matrix, make sure, I don't know what I have up in R right now. Oh, we actually have a confusion matrix. So there we go there. Literally one of the last things we did was confusion matrix. So there it is right there. So we were talking about this yesterday, and there's the confusion matrix. So you have to know how to read this. So when you read this, very important. Here's where, no. It's been a while. I've been working from today. Oh, how's it going? Where do you want to see where you're working at? Yeah, thank you, Alan. I was like, you're a former student. I just got over being sick, and good to see you, Sophia. Actual positive, actual negative, predicted negative, predicted positive, false negatives. And since male is level of interest in Alan, work at Pepsi. Oh, did you know that? Did I know that? Congratulations, Alan. We hope to have more students work there. Really good company. Really great company. Congratulations, Alan. Shouts, man. That's really cool. I hope you're loving it. My dad worked at Pepsi as his first job. I think it was his first job. You're welcome. Well, no, thank you. Thank you for sharing that. You're always welcome to come and speak. I want to get more students involved. Like, if you're still on the Discord and Pepsi has any openings, let us know. Because, hey, Zoe, good to see you here. So, Alan right there, working at PepsiCo, former student. Really proud of him right there. And, yeah, we've got a lot of people who, go and work for a lot of a lot of companies that hire data analysts, because you have to know how to analyze data. Do you use some of the tools and techniques, Alan? I don't know what you're currently doing, your current role. If you want to share anything in the chat, feel free to put in the chat. But Really honored that you're doing that. And I know Pepsi hires a lot of data analytics people. So we are predicting here. Why are we predicting female? I mean, why are we predicting male? My brain went to what I was writing. Why are we predicting male? Why are we predicting male? Why are we predicting male? So why are we predicting male? I'll give you a hint down here, and then we'll talk a little bit about this. The hint is because of that. So it's prob male. Hey, what's good to see here, Didi? We can look at the, and this is the accuracy of them all. Great job, Didi, right there. Whatever you want me to call you, Didi or River. But yeah, so good to see everybody today. I'm still recovering, cough drop and everything. And so the way that the model default does predictions is it defaults the level of interest to the last alphabetical. So there's really no reason we predict male. What is BAS? Business Analytics. Good seeing Justin. Oh my God, I got so many people here today. Justin, you're crazy, man. You're welcome, Brent. So in logistics, so say it with me, all the L's. Are you ready? In logistic, the what of what is what? It's all the L's. So if you remember this saying, in logistic, the level of something is this. So you can always remember how we do predictions in logistic by default. You can force in other ones if you want, but in logistic, let's see if anyone says it, but I'll say the whole thing in a moment. Helps you remember if you write it down or say it. In logistic, the level of interest is last. Do you hear the alliteration on that? In logistic, the level of interest is last. So it's just the way the algorithm does it. So we are predicting prob male. And so I'm assuming that this is sigmoidal up. We can look at the coefficients here of it in a moment. But with this, and so tools use Microsoft Power BI. Yeah, Power BI. We need to do more Power BI in our discipline. Here are polynomial models, regression. We do some polynomial, yeah. Yeah. So we'll do that here in a moment. Thank you, Zoe. In logistics, level interest last. Justin, great job right there. I'll show you some points for that. That is how we remember. Now, when it comes to indicators, the reference level is first. So that's the reverse of it. When it comes to indicators, the reference level is first. Like you don't see that one. We'll look at some models here in a moment and see that. But Didi was pointing out and so well that we predict people are male, and we might get correct that somebody is male right here. So this would be an accurate prediction, and these would be accurate. A lot of times this is called the on diagonal, and then the other one is called the off diagonal. The off diagonal, why? Why is it called the off diagonal? So why is that called the off diagonal? Think about why it's called the off diagonal and look at the combos you get. And if male is the level of interest, then a false positive would be predicting someone is male when they're actually female. So that would be a false positive in this instance. A false negative would be when you predict female, because the negative would be the not level of interest in this instance. It's contextual, like false positive, false negative. This one, what is a false positive, false negative? We can probably just call them both misses. But if we're predicting things like by, like if we change the context of this to and element OP, so let's put here by, and then let's put actual by, and then he'll put not by right here. Now, technically, our model is going to predict the probability of not by. More so, technically, model that matters to us, like in hospitals. Exactly. So, which one matters more? Because, and I like to talk about this, like with my sister, with selling houses. So, when you think about it, if she is predicting if somebody's going to buy a house, what is a false negative? Well, you would think that a positive would be you predict someone's going to purchase. So a false negative would be predicting not buy and the actual buy. So what happens when my sister looks at a client and predicts that they will not buy this house, but they would actually buy that house? Like if they're going to put up an offer and she predicts they will not buy, but they actually do buy. Thank you, Blake. Good seeing you, man. Oh, yeah, the same. I'm feeling better. So in this instance, this is a false negative right here because predicted the negative case. And so now you're going to maybe lose out on some business. If you predict not buy, then you're going to run the route of let's go the actions of this person would not buy. But in truth, they buy. So that's going to be a cost and you're going to lose on business. I'm going to send a heart to that nice Zelda text person. They're really great. And then the false positive is think about this. Now you're predicting buy, which is the positive action, the thing that maybe you're interested in. And with that, you're going to invest money into this. You're going to give showings of the house and do a whole bunch of things. No, might actually. Might pop. Oh my gosh, this is awesome. Oh, sorry, getting some really good text. Yes. That's a special person text me if you didn't know. Person. Really good news right there. Really good text from them. Like that. Anyways, personal life in the background. Type 1 error. Well, yeah, and type 1 error. So, and the problem we run into, and Dee can talk about this too, is I really like what, so they said, more specifically to the test accuracy of the model that matters to us. Like a hospital testing machine, a false negative could be worse than a false positive. So what we have to think about is explaining this. So let's say we are trying to figure out if something is contaminated. So you work in a hospital and you are trying to figure out if a medicine is contaminated or pure. Okay, so does this make sense, Blake, right here? So you have here predicted pure, predicted contaminated, predicted or actual pure. That means the vial you're giving someone, like whatever concoction you're giving, contaminated. Man, this is kind of scary, right? Well, hopefully we'd have better numbers than this, better accuracy of our model, and it's going to determine if this drug is pure or contaminated. So we want to make sure we're just giving things right here. So in a type 1 error, to use the terminology type 1 error, this is when the null is true and we reject it. So what would you assume? This kind of goes to what you have to assume for this hospital. Would you assume that your drug is good to go, or would you need evidence it's good to go? It's kind of hard to say, and that's what's like. You could have a hospital that's very, very particular and say every drug needs to be tested. We need evidence every drug is good. Or you could say when you bring it to this machine, you're assuming it's good until you have evidence it's bad. Like we don't throw away drugs until we have evidence it's bad. But another hospital could say we don't give a drug until we have evidence it's good. Does that make sense? Like here, Blake, while under the classical terms of statistics, why we sometimes, especially in the business world, don't say type 1 error, we might say false positive, and or we could just say we made an error. But type 1 error can get a little bit confusing because what is the null hypothesis? If the null hypothesis is this drug is pure and good to go, then a type 1 error would be when the null is true and we reject it. So the drug is pure and good to go. We're going to reject that. It was actually pure, and so we'd toss away the good drug. Now, if the null hypothesis was the drug is contaminated, so, oh gosh, then that means the null is true, it's contaminated, and we reject that and we say, oh, it's good to go, and we use it. So once again, and Dee pointed out so specifically, or people have been saying, it matters on the context. There's what kind of context are we dealing with right here? And then what was the null hypothesis that they're assuming? What are they looking for evidence of? And so sometimes it's easier, especially in the business analytics world, to talk about where are your errors. Does that make sense right here? To say it's very easy for someone to see we had 33 drugs that were predicted pure that were actually contaminated. We had 46 drugs that were predicted contaminated that were actually pure. So yeah, really good stuff right there. And when you look at this, I want to point out one last thing. What would the naive model predict for all the drugs? Good seeing you, Alan. Thank you so much. Yeah. Thank you so much. Yeah, because this is the context stuff right here where it matters, like making errors. And so what would you predict for all drugs right here, which would maybe be a good null hypothesis then? what would you think just theoretically about it? What would you predict for all drugs? Because these are calculations on your test. These are calculations on your test. These are calculations on your test. What would you predict for all drugs? What would you predict for all drugs? And we'll do some polynomial here, Zoe. I'll show the rest of what's on it. So if you look at the majority of drugs right here, the majority of drugs are actually what? The majority of drugs are actually what? Pure or contaminated? And how do you know that? The majority of drugs are actually pure or contaminated. All drugs are bad. Sorry. I got to throw you for that. Oh yeah, all Mars are bad for me, so I'll throw you some points for that. Well, and we would predict. So what is the misclassification of the naive model? Contaminated. Great job right there, DD. What is the misclassification or classification of the naive model? Great job, Madison. So this right here does not use the predicteds at all. We're only going off the actuals. Does everyone see that? We are only going off the actuals. So with only the actuals, we would get right the accuracy of the naive model is equal to 386 over 699. The misclassification of the naive model is the non-majority case. So the misclassification of the naive model is equal to the following. That is the misclassification. But now what is the misclassification of our model? Oh my God, I've totally made a mess of this. What is the misclassification of our model? This is all the naive. So that's the naive. Sure, something like that. And then our model. What is the accuracy of our model? What is the misclassification of our model? Now, misclassification is the complement of accuracy. So when you look at our model, now we are looking at the predicteds. So now you have to go into here for our model. So when you look at our model, how does our model do? These are the calculations and you know how to do. We did them last class or so. Gonna drink a little. Can you dry? See if you can solve these. These are good questions. This is what we were pausing on, what's on the test. So what is the accuracy of our model? What is the misclassification of our model? I think you're right, Sophia. Great job right there. Sophia, great work. So these are the wrong, and that's 79 over 699. And then you can subtract, because these values, when you solve them, should be what of each other? Like this value to this value, what should they be, Sophia? If you've done these properly, misclassification and accuracy should be what of each other? The naive will have its own same relationship, but what should these values be to each other? Like accuracy and misclassification are this of each other. They're, if you know, like, oh, the accuracy is the percent we get correct and the misclassification is the percent we get wrong. So they have to be what of each other. So you can kind of, once you find one, the other one's not that bad to solve for. What exactly? Great job right there. They're compliments. Great job, Didi and Sophie right there. Compliments, and technically compliments with an E. So technically, compliment with an I is like, great work today, everybody, and thank you so much, everyone, for being here. And it gives me more energy when people are here. And so, compliment technically with an E. I is the you're doing a great job compliment. So I didn't know that for a long time. See, Blake, I didn't know for a long time it's compliment with an E. We actually had it wrong in the Stats 1 notes for like 4 years or something. And then someone was like, oh, excuse me, I think compliments with an E. And I was like, oh, it is. Whoa, whoops. Our notes are wrong. So Blake knows compliment with an E. Never forget. So don't worry. I'm not going to, spelling is not my thing. Oh yeah, Blake, because you're 201, man. So there is. Thank you so much, Blake, for being here. We have logistic regression, numeric entry. So we should do some logistic general, logistic true false, multiple regression with categorical variables, multiple regression true false from Alan Panel. Thank you, Alan Panel. multiple regression in general, influential plots. Who knows some influence plots? Big brain right there. Interpretations. We might do another 201. I'll see. I'll try. I got some meetings. I'm gonna try to sleep a little more, but doing a little bit better. Head's a little fuzzy. Influential points right there. That looks like influence plot stuff. Well, there's influence points. Categorical variables, categorical variable indicators, multiple choice. It's a lot of categorical variable stuff. If there's time, could we do model hierarchy? Yeah, okay. So 2 questions. Thank you so much. Let's do let's do model hierarchy because you're right here right now, and then let's do polynomials. Okay. So here we go. Could you show an example if model was overfitting underfitting? Yeah, here let me show some overfitting underfitting. Yeah, here I'll put that. I got that on the list. There's the list. Got it on the list. So let's see right here. And I got some really good stuff with that, DD. I got some that'll really apply to this. And so the first question was model hierarchy. So when it comes to model hierarchy, taking the timestamp. Okay. So when it comes to model hierarchy, does model hierarchy have to be followed? First thing we need to know, does model hierarchy have to be followed? Does model hierarchy have to be followed? Does model hierarchy have to be followed? In 2 seconds, I'll be right back. It was cold this morning and it was getting hot. I was like, oh, it's getting too hot. So does model hierarchy have to be followed? The answer is a resounding so we don't have to follow it. So this thing I'm suggesting to you is like a guideline. It's like, hey, this is kind of nice. You should maybe do this. If you do it, it's kind of okay. Okay. So what is model hierarchy? Model hierarchy is this idea of there are more complex things. Model hierarchy is the idea that some terms that come into your model are more complex than others, i.e., they are based on kind of advanced ways of using the terms in your model. So there's more advanced, more complex terms in your models. What is model hierarchy? So when we do model hierarchy right here, it applies in a few different ways. Polynomial models. What is most complex right here? X to the 6th power or X? What is more complex? X to the 6th power or X? Which of those is more complex? Which of those is more complex? What is more complex right here? X is 6th power or X? X to the 6th power. X to the 6th power is more complex. So if we have X to the 6th power in our model, then what needs to be in our model? If we have X to the 6th power, okay, if we have X to the 6th power in our model, to keep model hierarchy, we need what? If we have X to the 6th power in our model, to keep model hierarchy, we would need what? So to preserve model hierarchy, we would need what? which is not required, but like if we have a model and show it over here. And so if we have weight, poly, and this kind of gets into poly, horsepower 1 and horsepower 2, data equals empty cars. X and Y differ in length. Oh, plot. Oh my gosh. There we go. Well, we need more than the 6th. And take a look right here. If you have x to the 6th power, then you would need x to the 1st through x to the 5th. And so the model automatically, when you do the polynomial, it automatically preserves model hierarchy. And you can see it right here where we have x to the 6th power, which horsepower is an x variable. And so to DD's point, this is probably, use poly for your y. I've never tried it on the y. What you would probably do is transform your y instead of doing a poly on it. Don't worry, that's not part of the take home. If you're doing the take home, I've never, whoa. It did change the model, didn't it? Interesting. I'm going to throw 1,000 points right there, Zoe. I've never tried that. I don't know exactly what that... I wouldn't do that probably, but that's interesting. You could transform your y before doing it, so we could look at the suggest transformations function for the model to do something like that instead, but that's interesting. So with this right here, you need the 1st through the 5th. So I think of it like building a tower. Does that make sense? Like if you preserve model hierarchy, you need x to the 5th, the 4th, the 3rd, the 2nd, and the 1st. And this is the preserving of model hierarchy right here. So this is, yeah, so you only use quantitative. We can only poly a quantitative. I've been talking to a few people on that. I haven't really told them how to do it, but I've been saying like you only poly a quantitative. Like you can't do it to categorical variables. Polynomials only work on quantitative variables. So that's my biggest hint. And then when you see it, you're like, oh, and you get it. And yeah. So polynomial models, if you have, so the key here is include all lower order polynomials. So the highest order is order 6 right here. So you have to include 5 and lower. And that preserves model hierarchy. So then there is the idea of interactions. You include everything in the interaction. So when you do interactions, it kind of looks like you're building a little Lego house right here. And so if you have x1, x2, x1, x2 interaction, so if you include the interaction in the model, then you need to include what? So this might help with the color coding on this. Like if you include this polynomial of this order, you have to include all lower order. But if you include the interaction, then to preserve model hierarchy, you do what? So let's say I have over here the model. And that would have been, I think we were going towards overfitting. River's talking a little bit about overfitting right here. And this is a major overfit model. We're starting to see it appear in the adjusted R squared, which we should also know what that is. But with interactions, let's do another variable. This is the cars data set, and we'll do by miles per gallon right there. Worked with a lot. Now let's take a look at it. This preserves model hierarchy because poly is the same thing as, yeah, it did to the 10th power. Exactly. It's yeah, that's exactly what it's doing. It's doing that variable to the 10th power, and it keeps the 9th, the 8th, the 7th, the 6th, all that right there. So it's really quick. It can do a very high polynomial model. We could actually take a look at what it looks like, but yeah, pretty cool right there. And so this one, interesting, it came out, whoa, wow. This actually is a really good model. Like really good. Like the variables aren't super significant, but probably due to some multicollinearity. Yeah, there's a good bit of multicollinearity there. So variable significance, I'm not too scared about. Usually when you do interactions, you hit some overlap because you're using a variable combination created from variables. So you're going to see variables stepping on each other's toes, which is the multicollinearity shown by variance inflation factor. And so with this right here, what do you notice? If you have an interaction, what do you need to include to preserve model hierarchy? So if you have an interaction, what do you need to include to do model hierarchy right here? If you have an interaction, what do you need to include to do model hierarchy? If you have an interaction, which this is the horsepower miles per gallon interaction variable right here. If you have an interaction, you need to include what to preserve model hierarchy. I'll give you a hint right here. I can choose to not preserve model hierarchy by putting them together this way in the model. So here's one that does not. This bottom one does not preserve model hierarchy. So this does not preserve model hierarchy, and the top one does preserve model hierarchy. So what is going on right there? What is the difference? So it kind of all the x's, that is true, but it could be something like this. So all the x's kind of, because you could have a model like this right here, and are all the x's required here? So this is another model here that does preserve model hierarchy, and are all the x's required here? So to preserve model hierarchy with the interaction, are all the x's required? Because it's very specific on what's required to preserve the model hierarchy. How would you know this preserves model hierarchy right here? Because I can make it not preserve model hierarchy by doing the following. Now this model does not preserve model hierarchy. So do you see what changed in my code that made this not preserve model hierarchy? Is it making sense, Olivia? Like what very specifically when it comes to interactions? Okay, so with this model right here, the key thing that you need to preserve model hierarchy is if you have an interaction with MPG and horsepower, you need MPG and horsepower in your model. Does that make sense? So when you have an interaction with X1 and X2, you need what in your model? If you have an interaction with X1 and X2, you need what in your model? If you have an interaction with X1, X2, you need what in your model? So if you have an interaction right here, you need what in your model? So if we have X1, X2 in our model, X1, X2 interaction, then we need what in our model? We would need X1, X2 in our model. So if we have an interaction, then the lower order terms need to be included. And so if you look right here, we have miles per gallon horsepower interaction. There's the interaction. And then right here, yeah, that's exactly it. Because if you have an interaction, interactions include everything in the interaction as their own variable. So right here, you'll notice what's wrong about this model. Look right here, it has MPG horsepower. It does not, like if you had to write a sentence, this model does not preserve model hierarchy because why? Because we did not include what in the model. And you can see the code on line 41 showing how it was done. This model does not preserve model hierarchy because it does not have what in the model? This model does not preserve model hierarchy because there's an interaction right here between miles per gallon horsepower. And so this model does not preserve model hierarchy because the interaction miles per gallon horsepower does not also have what? Horsepower. Great job, Sophia, right there. It does not have horsepower. So that's with a no horsepower in the model, exactly. And I subtracted off horsepower to remove from the model. So I purposely violated my model hierarchy. The last time to talk about model hierarchy is when it comes to indicator variables. Include all levels. Yeah. Sure. So when it comes to an indicator variable, if we have sort from a hierarchy, all variables need to be represented. It just depends. So Zoe, it depends on if you have a polynomial model and you have an x to the 6th power, that same x needs to have all of its lower order powers. If you have an interaction and it's between x1 and x2, then x1 and x2 individually need to be in the model. And if you have an indicator variable, like let's say here, day of the week, 1, 2, 3, 4, 5, 6. And so you have, no, day starts with lunes, or Monday. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Okay. So if you have an indicator variable, then what will be the reference level of day of the week? What is the reference day of the week? What is the reference day of the week? So what is the reference day of the week? Friday. Great job. Awesome. Because it's the first alphabetical. So Friday is the first alphabetical. Friday doesn't get included, but everything gets its own indicator. This is preserving model hierarchy with indicators. And so if an indicator is removed, we do not preserve model hierarchy, and the new reference level is the reference and that indicator. So with this right here, if we were to remove something like, if we were to move Tuesday, Wednesday, Thursday, then what would happen to this model right here? If we were to remove Tuesday, Wednesday, Thursday, then what would happen is we would have the new reference level of all these days. And then there would be indicators for the following. Does that make sense right there? Yes, that's because alphabetical. Yep, that's why it's the reference level's first alphabetical. That's correct for reference levels. But so this is the violation of model hierarchy with indicator variables. When you have 6 indicator variables to preserve model hierarchy, you need to include all the indicator variables. If you remove out indicator variables, where do they go? Everything starts to group up with the what. So this is big right here. If you remove out indicator variables, they all start to go to where? If you remove out indicator variables, you have to make predictions for them somehow, so they all become part of the what. They all team up with the what level. If you remove out indicators, they all go to where? Any indicator that's removed, like if I were to remove Sunday also, whoops, we can't do that apparently. If I were to move Sunday or anything, where would it go? It would become part of the predictions that it would all be one level, known as the what level. Indicators that are removed, anything we don't have an indicator for is now part of the what? The reference. Anything we do not have an indicator for is now part of the reference. So that's how it works. So I think it was Sophia who asked this. These are the 3 ways in which model hierarchy apply with polynomial models, with interactions, and with indicator variables, or polynomial x's. And notice this all only deals with your what variables. Model hierarchy only deals with your what variables. So model hierarchy only deals with your what variables. It only deals with your what's is, because this is indicators with reference levels. It only deals with your what variables. Another good thing to know, it's like, oh, it's dealing with my these, and I have to put the ones that are less complex in if I put the more complex ones in. Kind of having all the components. Well, these are categorical down here. These are categoricals. These are categorical x's, and everything is all what's is, because these were just unnamed. These are everything is x's. Everything is x's. Logistic models. Can I think on myself confused? What is the thing? That's how many indicator variables there will be. So if you have 12 months of the year, then there will be 11 indicator months, and there will be 1 reference month, which I think is April. Yeah, that's first alphabetical. So the reference month is April. It's just arbitrary. It's just the way the algorithm runs. You can force in different reference levels if you want, though. You could technically do that. Then we have the next question, which is polynomial. We did a little bit of polynomial. So I'll speak briefly about polynomials right here. And then we got some overfitting. And then we got more questions. Put more questions in the chat because polynomials won't take too long. So when it comes to polynomial, the poly function is very important. But you want to know, and this is huge hints for the take-home especially, when you deal with polynomials. All right. And why can I not do a polynomial? Who knows why I cannot? Let's try a poly right here. Why can I not poly that? Why can I not be influential points? Yeah. Influence points. Let's look at influence plots here in a moment. Influence plots. Gender is categorical, exactly. So if you want to see what your data looks like, you can always go over here and take a look and see what you got going on. Gender is categorical right there, so we can't polygender. So you just can't. The function doesn't work like that. So make sure you look at your data over here and see what you got going on, see what you're working with. That will help with dealing with any issues the data might have. And you could do like poly of weight, and there's the second degree polynomial. And there we go. Now, as we said, we could start going crazy right here. And wow, look at that. That's interesting. How is it actually going higher? Woo, 2 unique points. Shocked it's still going up. Because the next, and so I think there's not much to polynomial other than that. Well, I guess I'll show one last thing with it, because one of the best ways to think about the polynomial order is to investigate it in the simple world. And we can go right here and we can make the choose order function, one of my favorite functions to do, which is going to allow us to choose the correct polynomial order for a simple regression. And we can see what's going on right here, where there might be some sort of weird bend. I don't know, it's pulling towards the outliers. So you got to watch out, because are you fitting the data or are you overfitting the data? And that gets into some big topics, which we get into 474. So when you talk about overfitting versus underfitting, if you increase the polynomial really high, you're going to go towards overfitting. But we're going to go into a little more detail on that here in a moment. We'll go max order. Does it make sense? Now, how can we kind of look at this and think about, are we overfitting here? When would we think about this and say, are we overfitting? There's actually some really good output that probably is going to be the closest to the truth. So when would we think about overfitting right here? So what is the most underfit model right here? And I wonder if oh man. Oh, I have to say H equals. Yes. Okay. So order 1, but I just added in something else. What did I just add in? If you look at the code, I just added in something else, which is the most underfit model. It's probably pretty accurate. Like, the linear model is probably pretty good, but then I also added in something else. So, and I think I can move the thing. Is it loc? There we go. Okay, so now I got the graph I want. Correct. Choose order, the red line. So what is the red line called? What code did I use to get the red line? So the code I used for the red line was AB line, which draws a line, horizontal equals mean of survey 10 height. So it's not in order. Good answers right there in questions. It's known as the what model, and this is the most underfit model there is. So this is a model that actually doesn't use the x's and has a very specific name for it. So this is the most underfit model that does not use. It is the mean. So it's the mean of the x's, or the mean of the y. Excuse me, I said x's. It uses no x's, and it's the mean of y. When you use the mean of y to make predictions, you're using the what model. We mentioned this earlier, and it's different in logistic. So I mentioned the what model over here. The mean in quantitative is known as the what model. So the mean of the y variable is known as the what model in just quantitative regression. The naive model, yep, that's the naive model. So the naive model is the most underfit model we usually have, which it doesn't even use x's. So when you think about underfitting and no, that's exactly it. It's a great job right there. We got to throw some points for that. And you're all right. It is the naive model. So when you think about it, when you talk about underfitting versus overfitting, underfitting is when you take too little information from your x's. So what is the way to take the least amount of information possible? You don't even use information from the x's. You only use the mean of y, which is not a horrible model. That's actually where the sums of squares error calculation comes from. The total sums of squares is calculated from the naive model, and then the reduction in it is seen. I could try doing, Daniel. I think we could. Maybe later tonight. I'm going to rest up here a little bit. Actually, I'm feeling pretty decent right now. So why not just have another cough drop, right? Why not? I'm just going to treat myself to this cough drop. We did some yesterday, though. Check out yesterday's. I felt like we didn't do enough 320. But thank you everyone here, 320. Daniel, good to see you. So with this right here, the most overfit is going to be, or the ones that are probably going towards overfitting, are going to be the high polynomial. And so Daniel, how would we figure out which way to go on this? If we're making predictive models, then what would we need to look at? Because we have a way of looking at this, and I might not run the code for it, but we need to do what is called cross-validation. So cross-validation is the technique of making your model on a certain portion of your data. We're going to mention this briefly right here. This is the k-fold cross-validation process. And so this would be k equal 4 for the k-fold cross-validation process. And the k is the amount of folds you're making. And so you would make your model here, and then you would test your model there. And we make the model on a party data and then hold a party. And so what you want to see is when you make the model over here, does it then work on this portion? And it's called the k-fold cross-validation process because you do 4 rounds of it also, where then you switch up where you make the model on these portions and you test it here, and you just permeate through. Now, what you get from this is you would get RMSE of round 1, RMSE of round 2, of round 3, of round 4. And so you might have a typical miss of 48, 49, 47, and 50. And from this, you could then find out, was I nice to myself? I don't think I was. I was trying to go like high-low, high-low. Oh, no. Can't do maths. There you go. From this, you could get a mean, and you could get a standard deviation. So your mean RMSE would be 49, and standard deviation is probably something like, am I going to be right? It'd be funny if I knew that one off the top of my head. So RMSEs, and it calculates these for you, your typical misses. So you don't have to do this work. 1.1. I can't do a standard deviation in my head. And then we can figure out, on average, what we think our model will miss. Error does not like multiple responses. What code did you try running, Zoe? And so, to River, your question, basically on overfitting, underfitting, this will give us confidence that we have not overfit because the model was made on this portion and then the RMSEs are generated on the test portion each time. Like each time we get an RMSE, this would be like from round 2, where it was made on those 3 portions and tested on the other one. So we're not overfitting it to it. Now we have an additional thing we use, which I think Daniel's basically pointing out right here, is we also have a holdout. And so the holdout is data we leave out of the model, and then we test it on that data when we finish. So that is not part of the k-fold cross-validation process. That is additional data that we take at the start and remove away to then see how it does. So at the very end, we get a final check called the RMSE holdout. And the RMSE holdout is usually a little higher. Let's say it's 51, but it should be about similar. We don't like it to be about 5% higher, but the RMSE holdout is going to be how it does on new data the model hasn't even seen before. Because in the k-fold cross-validation process, we use what's called a pseudo holdout, where we kind of hold out part of the data in one of the rounds of the k-fold cross-validation process. So in this second round of it, this portion of the data was held out. It was made on these 3 portions of the data, and then we find the RMSE of the model. And so then we find out the typical RMSE, and then we find out the standard deviation for the variation in it, and then we see kind of how it does on new data. There was another question. Influential plots. Oh, we just overfitting underfitting. I think I was at 53. Okay. Influence plots. And so he's going to tell me which thing her code went to. Influence plots. Okay. Influence plot. Okay. Let's go here to influence plot. Here's an influence plot. Sorry to step away. Did you explain this? But what did that come from? I don't know if you can tell me what code that came from, what you typed in, as long as it's not like giving away a test answer question. Let me know, Zoe, right there, and I can go into detail on that. So what does an influence plot show us? Well, it has 2 key concepts right here: a deleted studentized residual and leverage. So when it comes to leverage, let's talk about what leverage is. Leverage is literally the idea of a seesaw. Try to use poly. Oh, and then you might have it for, you have to use only X models with 1X, and it has to be quantitative and 1X. So which of these points on here has the most leverage? A, B, C. Which of these points has the most leverage? Which of these points has the most leverage? It would actually be A. So A, if you think about, if you were to take a hammer, so imagine you have a hammer, and I'm going to ask you to slam the hammer down. So I give you a hammer. I'll give you a big hammer right here. And I say, take this hammer and slam this hammer down. Slam this hammer down wherever the spot is. Does that make sense? You're going to slam this hammer down wherever the spot is. You can go right here and slam it down right here. Or we're going to slam it down right here. Where is the seesaw going to spin the most when you slam the hammer down? Where? On which spot? Where would it spin the most? So leverage. So what does this fulcrum here represent? In my diagram, what does that fulcrum represent? What does that represent right there? Where did I try to put it? DD, I think we might actually be, that's the mean of the x or the x's. In the multivariate world, it can get a little bit complicated. So that's the mean of the x variable. And so now you might be thinking B's got something unique about it. B and C have a large what? You don't have to say the full thing, but B and C have a large what, which is their unusualness and their y. B and C have a large what? We probably need to add some points down here or something to make this more of a linear model work. Okay, that might be enough so the model works. C actually does not have any good answers, Peyton, right there. B actually has probably the most influence. C has no influence and A has no influence. I'll explain why they have no influence here in a moment. But B and C both have for sure what? And look at the graphic over here for answers on the y-axis. What do B and C have? What do B and C have? They have large residuals and a deleted studentized residual. The studentized portion means it's on a student t distribution. So you see the classic -2 and 2, where 95% of the points would be contained between on the normal curve, or 95.449 technically. And so deleted, studentized, and the deleted part means if you have a point over here, it would take the model and make the model do this. But if we delete that point, then the model is going to look like this. So this is the deleted residual, and this is the residual. So the residual is how much we miss by, but a deleted residual means we what that point. So why do we call it a deleted residual? So we call it a deleted residual. We what that point from the model, and then we redraw it. So literally, you go in there, and what does it mean to say it's a deleted residual? The deleted residual will what? So that's the residual right there. It's just very small. It's how much the model misses by. But the deleted residual is when you delete it, and then because of that, the line will not go towards the point because the point has no influence. So you can see the deleted residual here is much larger. Now the studentized portion, once again, just means it's on a standardized scale, so that -2 and 2 are always more extreme. Because 95% of observations on the normal curve would be expected to fall within -2 or +2 standard deviations. So we studentize it to basically standardize it. I wish it just said standardized, but it's studentized because it's student t. But you could call it a deleted standardized residual. Probably no one would care that much. And so now when we look at this, these are points with high leverage beyond this line right here. And I don't make you calculate that. These are points with high deleted studentized residuals beyond these points. So the points with high influence are going to be these 4 points right here. And the size of the circle is the size of the influence. There are some points that probably, have a little bit. So there's a 3. No, there's a 4th right here, right? And then this point, the reason we get this plot is you might look at that one and say, question mark, maybe that one's got a little more influence than we like. And what does it mean to have high influence? It means the model is gravitating towards these points and being pulled in their direction. And some of these points, like if you remove this point right here, what's going to happen to your model? That point that I'm highlighting right there, because of its no influence, what's going to happen to your model? If you remove that point right there, if you didn't have that point in your model, what would happen? And this is what influence means. That point, that little dot you can barely see on there, if you remove that, the size of the circle is the size of basically your model wouldn't change at all. As The Rock would say, it doesn't matter. A point basically has no influence on your model. It's not doing anything. But these points down here, you remove them, the model dramatically shifts. Considering that there's like 699 points that make up our model, do we want 4 points having a lot of influence? Sorry, negatives. Oh, yeah. That just means to pull them all down. Something can be very influential and have a negative residual. Do you want 4 key points that are kind of dictating your model? I mean, if you look at the size of these, like planets in the galaxy, they're as big as like this. These 2 planets right here are heavily influenced in the model. Like they're a major influence. You remove out those 2 points, and the model is probably going to dramatically shift. We don't. So we say QQ straight enough, no outliers. This is kind of the look at the outliers. So the 2 things you need to be influential are you need leverage, and you need a deleted studentized residual. So take a look at this point right here, point C. Point C has absolutely no what? Point C has absolutely no what? Near 0 what? Point C has near 0 what? Point C has very little to no what? It would have no influence because it has no what? Which is weird. It would have no influence because it has no what? No leverage. It's on the mean of the x's. What it actually does is it doesn't change the xy relationship. It would actually pull the line upwards. So it's not going to like turn this teeter-totter. It's going to pull the line up towards it. Does that make sense? So it has no leverage. Point A has no influence because y? Point A has no influence because y? Point A has no influence because y? You're like, so if we look at influence, point A doesn't have influence because y? You can be very specific, like what actually makes influence. It's on the line, which means it has no deleted studentized residual. So its residual and deleted studentized residual is close to 0. So it's going to have no influence, even though it has leverage. So basically, if it's on the line, it really can't move the line. What is the name of the line? It's the regression line, or the line of best fit. And it doesn't work quite this way. The way I see it in my head is there's an equation of sorts that's like deleted studentized residual times leverage equals influence. This is not the way it works. I'm totally not showing the real math behind it right now. We could look up Cook's D and all the good stuff. Cook's distance, the stuff you need to do. I think we just write. There we go. And there's all those good things right there. Won't go that technical on it. So if leverage is 0, influence is going to be what? If leverage is 0, influence is going to be what? This is not the real math, but it makes sense conceptually. If leverage is 0, influence is 0. If deleted studentized residual is 0, influence is what? Does that make sense, Peyton, seeing it this way? To be like, if either of those are 0 on the other side, then influence is 0. So when you look at it conceptually down here, this has no deleted studentized residual, so it has no influence. So it's not directly calculated that way. Like the computer will do all the calculations for you. But yeah, I think Cook's distance, I think that is Hat's matrix. I haven't used technical terms in a while. Look at all the references. Good stuff. A lot of fun stuff. You don't have to know Cook's distance. I think we had one more question, right? We just did influence plots. And then you should know like how many points are influential and which quadrants are influential right here, like high leverage. Like, can anyone tell me, is there a final more considerable? It's a lot of knowing the output. It's a lot of like knowing output and knowing what everything means, knowing how to interpret coefficients. Like if I make output like this right here, you should be able to know every bit of this output. Like, could you quote and explain every, this is just a simple regression model right here. It's a lot of output driven, a lot of like knowing output, knowing what we see, knowing how to explain it, a lot of multiple choice, but knowing output, which we always stress, like, could you explain to someone what every value means? Like, this is the formula used to create the regression right here. The y variable was height and weight. Can you give variation between leverage and influence? So influence is how much the model is impacted by a point. So if a point is influential, then the point changes the model. Does that make sense with Zoe? Say if a point is influential, then it changes the model. Like, that's what it means to be influential. I'll tell you momentarily. When we say a point has leverage, that means it is far from the what of the whats. If a point has high leverage, which I think we can just run leverage on it, right? Not leverage. I thought it was leverage. Check for leverage. We'll look at T here in a second. If a point has high leverage, then a high leverage point is a point that is what? Like, this point right here is the what is from the what. That point all the way over there, you see it right there, that point all the way over there is that point right there. How'd I know that? That point right there, not just because it's on the right, got to watch out because points over here can flip around. This point from the mean of the x's, it's the furthest from the mean of the x's. So you have to watch out because the mean of the x's, this is where leverage can be a little bit confusing. The mean of the x's, I believe, is about here. So with the mean of the x's being there, then this point right here, do you see these 3 points? Let's go find those 3 points in the other plot. Those 3 points are probably over here because the mean of, it's hard to say where they're at. They're probably somewhere in here. Yeah, I think that's them right there. Because we would need to go a little bit away from the mean of the x's, and it's going to fold over. Like, this whole thing is folded over onto it this way because it's just seen as a positive difference. Does that make sense? Like, you would need to literally take this graphic right here and fold it over on top of itself. Actually, it'd look like this from your reverse angle. So you need to fold the graphic on top of itself, and then the points distance from the mean of the x's are their leverage. So the points would be folded on top of each other. Oops, oh my gosh. And that is going to be the leverage. Does that make sense? So how far you are away from the mean of the x's is your leverage. So the t statistic, does anyone know what the t statistic is? Why do we primarily have t statistics? Why do we primarily have a t statistic? We primarily have a t statistic to what? Why do we primarily have a t statistic? Like, in classical statistical sense, why do we primarily have a t statistic? T statistics are found why? Why do we have t statistics? We have t statistics. Why? One of the key reasons to have a t is to find the p-value. So you can actually tell which p-value is smaller by looking at the more extreme t statistic. How do you calculate a t statistic from your estimate and standard error? So the t statistic is the standardized metric by which we can compare things. And so the t statistic is just the estimate divided by the standard error. For this, from the error, so larger t statistics are further from zero. So when we have a t statistic that is more extreme, you can see that they're more unusual. So this graphic's kind of doing the same thing. Is it from the null hypothesis? Well, so a lot of times, especially in business analytics, we don't always talk about the null hypothesis. The null hypothesis for all of these would be that the coefficient of intercept is equal to 0, the coefficient of weight is equal to 0. We can reject both of those. The more important one here is the The more important one here is the weight coefficient, because weight is the x variable, and the x variable makes the model. Fun fact, if you didn't know it, if you square the t in the simple world, one of my favorite fun facts, you actually get the f statistic. So you can see right down there, it probably didn't carry enough decimals, but if you square the t in the simple world, you actually get the f. It's just a weird, fun concept. So with this, no worries. The t statistic is a standardized metric for us to see if our result is unusual. T's more extreme than 2 or -2 are pretty unusual. We don't have to worry about calculating whether or not it's unusual because it's going to do all the work for us. I think I had some models earlier with the car data, which were pretty interesting. It was just the one with the interaction. Because if you go back to your 201 knowledge, take a look at these t statistics. You get a t statistic of 1.96 basically, but you have to watch out because t's are not like z's, and then the p-value is very close to 5. Because remember, 68, 95, so 5% would be outside. But the t statistic is based on degrees of freedom, and so when you do the t, it matters what the degrees of freedom are. And degrees of freedom for this are, is it 28 degrees of freedom? Might be around that. And so we would put in here 1.95 with 28 degrees of freedom. And it looks like there is the calculation of, yeah, there you go. You can see it right down here on the bottom, the 0.061. So as you can see, when the t gets more extreme, the p-value gets smaller. And this is the absolute value right here. So we're trying to see if our result is unusual and unlikely by random chance. We don't care about the intercept. But a lot of times in the multiple world, we're not so interested in the individual variables. We're interested in the overall regression down here with the ANOVA. So the ANOVA is being run down here on the bottom. We could simply run the ANOVA by itself, and it is giving the p-value for each individual thing. Sure, fun times. But the p-value for the overall model right here is very, very small, telling us the overall model is significant, that it reduces the sums of squared errors in a significant way. The other thing, why do you think these variables are barely not significant here? We mentioned this previously. There's a follow-up question. So we need to find the t with, could just find the, it's easier, like if these were blanked out in the output. Well, so you can't do that here. For this output, it only works for the simple world. But if I said find that t statistic, could you do it? Find the t statistic for miles per gallon, could you do it? So if you had to find the t statistic for miles a gallon, could you do it? So you can't use the f trick here because it's the estimate divided by the standard deviation exactly. So you just divide. It's just a standardized metric. Because think about this. Like if I said, is the intercept large right here? And let's talk about this briefly. The intercept is the largest value, but it also has the most what with it. The intercept is the largest value, but it also has with it the most what? Like, what is standard error? The intercept is the largest value, but it also has with it the most what? SE, but what is SE? What does SE mean? So the way SE goes is standard error is our amount of what in our estimate. Well, RMSE is down here. RMSE is the root mean square error, which is that. So that's different concept down there. RMSE is root mean square error, the typical mistake model makes. And so standard error is like when your friend says, dinner will cost about $30, but in uncertainty exactly, but I could be off by about $2. So if your friend told you, we're going to go to a fancy restaurant, it'll be about $30, but I could be off by about $2, then would you be shocked if it cost $33? Your friend says, dinner will cost about $30, but I could be off by about $2, and it ends up costing $33. Are you going to be shocked? Are you going to be shocked and be like, what the heck? You'd be like, it's kind of close, right? I mean, they're not saying they will be off by this. This is just a metric of, you're like, that's a little bit more, it's a little bit unusual, but think about the t statistic. What would the t statistic be? Oh, so do this right here. What would the t-statistic be? And this will, then you'll see like, oh, wait a minute, it's not beyond 2, right? So what would the t-statistic be here? So if you're following along with how this works, calculate the t-statistic for how shocked you are. The standardized metric. Calculate the standardized metric. Not 15. I mean, you might check your decimals. I think you're on the right track, Peyton, because there's a decimal shift that you'd be right on. So how much were they off by? So they were off by what? So you would say here, there we go. Does that make sense? They were off by 1.5 measures of uncertainty, which I do agree is a little like, but it's not that weird, right? It's not that weird. But what if it cost $40? Now, if it costs $40, now they're off by how many measures of uncertainty? And they'd be like, come on, man, I was only off by $10. And you're like, but $10 was what of your uncertainties? And this is why it standardizes it based on their uncertainties. So now that's a measure of 5. So they're like, it was only $10. And you're like, but you said you had an uncertainty of $2. That's 5 uncertainties. I standardized your miss. So now this is a rather large miss and very unusual. So 1.5 is going towards it. That p-value on that's like 12 or 13%. We could go back here. If we're talking the same world we were just in, and we go in and put in the t-statistic of 1.5, it's 14.5%. So I was like 12 or 13, somewhere around there. So it's kind of unusual, but it hasn't reached that 5% or less that we think is pretty unusual. So around the point of like $34.2, we'd be saying this is really weird. So it is reaching that range. It was in that kind of iffy range, but yeah. So we have t-statistics to put everything in context, because even though the intercept has the largest value, it actually has the most uncertainty. So you would say something like, oh my gosh, the interaction is so small. That can't really play a role in this model. But the interaction's uncertainty is also very what? Like the interaction is very tiny, but the interaction's uncertainty is even tinier. So we're like, this is the role we think the interaction plays. And you're like, but that's nothing. And you're like, but we have very little uncertainty in what it plays. The uncertainty is even smaller. So you can't be like, oh, the interaction's nothing. It's so tiny. But we have very small uncertainty in it too. So that's why you have to compare, and it standardizes things. So the t-statistic is a standardized way of looking at everything, and then the p-value is the probability of its probability of the result you saw. Results from machine happen by random transformation, given that the null is true. It's gonna cite the temperature textbook. What other questions are there? We've done a lot right here. Might head off and do some forcing for later. What other questions are there besides interpretation and knowing the output? Is there anything else to focus on? So what I noticed was, under the modules, I've got here. That's wrong class. Under those modules, and I think everything's graded. I'm gonna be working on grades a little bit later today. So thank you to the grader getting everything graded. We love that. And interpretation coefficient help. What? I think this has it mostly. Yes. See right here. This is something I uploaded a while ago. So is it simple or multiple? If it's multiple, otherwise identical must be said. Is why quantitative or categorical? Quantitative, interpret the coefficient. Categorical, do not interpret the coefficient. Only mention increased or decreased probability. Is X quantitative? Yeah. This has been posted. I posted it right here. I posted. Differ by, so quantitative, differ by 1 unit of X, expected to differ by. So make sure to give the context where the blank X is expected to have the blanker Y. One is the level of interest, and the other is reference level. The indicator is expected to be B1 US. Where the higher X is more or less likely to be Y. So, but you need to practice this. So here, I'll do one right here. You ready? So you need to practice this. You need to make sure to have it down. because if you don't know how to use the cheat sheet, it's tough. Okay, so what should you immediately notice? Because I think, let me look at something. I'm going to cheat. Let me look at something, because this is a big hint if this is true, and I think it is. Oh, give me a second. Where I want to go. I'm pulling up the test in the background, if you're wondering. All right, so I'm going to go look at the test, because I'm pretty certain of something. Pretty certain. Pretty certain. 2 seconds. Here we go. Okay. Yeah. Yep. Okay. Let me close out of the test. Okay. Don't be shy. Show the test. Okay. What should you immediately notice about this right here? What should you immediately notice about the code I'm writing? What should you immediately notice? You won't tell. What should you immediately notice? It's logistic. Boom. Yeah, exactly. And so you know it's logistic. Okay. I'm giving you a hard one right here. It's like if you can do this, interpret the coefficient of handedness left. Interpret the coefficient of handedness left. This is probably one of the hardest ones you could do. So if you can interpret the coefficient of handedness left, then that is like the combo of everything. Like it's knowing exactly what to do with each component of this. So I'm going to give this a moment right here. We'll throw out some 5,000 points. People get it right. 5,000 points you get it wrong. Give it a shot. So it's logistic. It's also multiple, and that's an indicator. So what would you write? About 2 minutes ago, I started doing, man, I did more than influence plus, right? Interpretation. Okay. 2 individuals who are otherwise identical. One is left hand, one is ambidextrous. The individual is left. Peyton. I lied. 50,000 points. Why not? I think that's exactly right. 2 individuals who are otherwise identical. One is left-handed, one is ambidextrous. The individual who's left-handed is more of a male. That's it. That's all it is. That's it. And because ambidextrous is the reference level, the one you don't see, male is the level of interest that we're predicting for because it's last in logistic, and then you don't mention the coefficient. And since it's positive, it's more likely level. Peyton, is it making sense? Like, I think when you do it multiple times, when you practice it multiple times and you start to get it down, it starts to make sense. And you're like, oh, so if we have 2 people who are otherwise identical, but one's left-handed and one's ambidextrous, the person who's left-handed is more likely to be male. Otherwise identical meaning they're the same height in this instance. You don't have to say that, but there's only one other variable. So you could technically have said 2 people who are the same height because that's the otherwise identical. It's just in the multiple world when there's a lot of X's, it's too much to be like they're the same height, the same weight, the same this, same that, same this, but one is this and one is this. Trying to think of how to trick you. Good to see you, Rhea. Yeah, are you doing practice final like what you did with the midterm? I didn't release it. Maybe I don't want to, I'm a little afraid even as a bonus or something. Sorry, I've been so out of it. I'm going to try to get grades finished up today because the grader finished grades. And then, if not, going to be super, hold on. I might have one ready to go, but last week was just like wrecked. Like literally, I feel like I lost a week. like for 2 days, I was basically in bed. My wife was like, "Don't like." I didn't want to get out of bed, but she was like, "You need to lay here." So, do I have one? I don't see it, so maybe I don't even have it. Oh yeah, it's the worst. It's the worst sick I've been in my adult life, probably, which sucks. Like, I can't think of the last time I was this sick. It sucked. Like, when I woke up on Wednesday, like, I started to feel Tuesday I was gonna play some video games. Usually I play some video games a little bit at night. Like, it's like 10, 11. I'm like, I'll play a little video games here. And then I was like, no, I gotta lay down. And then I laid down just and then what sucks is earlier I didn't have a cough, and it was just like waking up hot and sweaty. Is RSV as bad as Texas? What is RSV? I don't know what RSV is. I don't know. It's probably pretty bad down here. Whatever it is. But it was like, what's tough right now is like I'm sleeping like 9, 10 hours a night because I'm waking up and like coughing and stuff, and like just being like, okay, don't cough, because when you cough, you just seem to irritate it. I think it's like the strat right there. I'm trying to speed run this, and yeah, I don't know what RSV is. What is what is a CDC thing? Okay, RSV, respiratory syncytial virus. Oh my gosh. Oh, recover in a week or two. Yeah. Well, it sounds like maybe it is. Yeah. Syncytial. I can't even pronounce when the things there should be a pronunciation for pronunciations for me. Yeah, maybe I had this. Yeah. I mean, like it says recover in a week or two. That's, like a lot of things take like 7 to 14 days to recover from. So I'm on day 5. It hit like Tuesday night. So yeah, I'm on the upswing. I'm on the upswing, but I wasn't really doing much until like I was replying to emails and stuff and Discords and everything I could, because if I didn't do that, I would have came back to whoa. So basically I'd get out of bed and do computer stuff for like an hour, and yeah, but I just tried to like ride the wave of things, and so yeah, but yeah, I had to feel like 3 weeks ago. It was rough. Thank you so much, Payne. Yeah, it is rough. And whenever you have trouble as a student, please reach out to the Dean of Students, or I'm glad that I'm just like, I'm almost feeling like I need to eat more food. That's what I need to do. Like made a pizza and ate like a whole pizza in a day. It's good adult decisions right there. I'm very good at adulting. I'm like, what's for lunch? Pizza. What's for dinner? Pizza. What's for breakfast? French toast sticks with syrup on top. I'm an adult. Anyways, I must talk less about adulting. We'll go over to the main screen. A lot of 320 review right here, a lot of concepts. Please check over the classes because we cover everything. So it's hard to cover everything here. Pizza in the morning, pizza in the evening, pizza at supper time. I need to get that pizza on a bagel so I can have pizza anytime. Hey, Robert, thanks so much. What is the difference between analytics and statistics? So analytics is the key buzzword. Statistics is like the old-fashioned kind of classical idea of mathematics, but analytics is more applied. So I would say when you talk about analytical skills, you're talking about like more, software and ability to work with data, where statistics is kind of the classic of like hypothesis testing. Statistics is more of a classical sense to it, where analytics, like things like big data, when we talk about like handling big data or AI, I would say that's more analytics than statistics, where statistics is more like standardization of stuff. And so to me, statistics is more of a classical idea of classical tests to analyze and understand relationships in data, where analytics is high-level techniques with modern computing power. So to be good at analytics, you would need you need to leverage computer knowledge. To be good at statistics, it might be better to be better at math, because statistics can be more about statistical theory and math theory and number theory and set theory and all that good stuff. So statistics is more math-based, analytics is more technology-based. Because, yeah. You're welcome, Zoe. Good work right there. I hope that helps, Robert. Does that make sense? Analytics is going to be more tech-based, and statistics is going to be more math-based. Both use tech and mathematics, but you're going to lean more. If you're stats, you're going to lean more math. If you're analytics, you're going to lean more technology. Like, I can see a statistician who really uses little software. They're not doing like high complex stuff. Like, my dad was that kind of statistician. So I've got that sort of luck. I've got my dad being a statistician to help me know. He didn't do like simulations and stuff. Hey, maybe he didn't know he had a simulation software. What am I saying? He didn't do bootstrapping. He didn't do big model predictive analytics. It's just what you do. It's who you are. With that, you're welcome, Robert. Thank you so much. Until then, bye for now, everyone. Bye.